Okay, let's start diving into the world of interrupts and interrupt handlers. Okay, I think we read all of this already, so let's just do it again. A core responsibility of any operating system kernel is managing the hardware connected to the machine, hard drives and Blu-ray discs, keyboards and mice, 3D processors and wireless radios. To meet this responsibility, the kernel needs to communicate with the machine's individual devices. Given that processors can be orders of magnitudes faster than the hardware they talk to, it is not ideal for the kernel to issue a request and wait for a response from the significantly slower hardware. Instead, because the hardware is comparatively slow to respond, the kernel must be free to go and handle other work. So dealing with the hardware only after the hardware has actually completed its work. How can the processor work with hardware without impacting the machine's overall performance? So like how can the computer still account for the hardware while running your programs at the same time? One answer to this question is polling. Periodically, the kernel can check the status of the hardware in the system and respond accordingly. Polling incurs overhead, however, because it must occur repeatedly regardless of whether the hardware is active or ready. A better solution is to provide a mechanism for the hardware to signal to the kernel when attention is needed. This mechanism is called an interrupt. In this chapter, we discuss interrupts and how the kernel responds to them with special functions called interrupt handlers. So, interrupt handlers are how we respond to interrupts. And these interrupt handlers are special functions. So, we run these interrupt handlers whenever an interrupt occurs. Okay, interrupts. Interrupts enable hardware to signal to the processor. So enables hardware, the hardware you have in your computer, to send things to the CPU. So if you had a CPU here, let's just draw a CPU, and then you had memory. The heck am I thinking? You had RAM. Then you have basically a bus that goes between CPU and RAM. You'll have actually, peripherals. So I/O, PCIe, and so on. And that is all with through the CPU. Something like this. So this is like your basic computer, right? Your computer should be able to function with just processor and memory, but then occasionally you want to do stuff with other devices. So that's how you actually communicate through these buses. And then every once in a while, these devices will send interrupts to the CPU, and CPU will do something with those. So interrupts is like, hey, I have something for you, CPU, from the device. All right. So, for example, as you type, the keyboard controller, which is the hardware device that manages the keyboard. So, you ever opened up a keyboard, there's like a small chip inside. That's the keyboard controller. It issues an electrical signal to the processor to alert the operating system to newly available key presses. These electrical signals are interrupts. The processor receives the interrupt and signals the operating system to enable the operating system to respond to the new data. Hardware devices generate interrupts asynchronously with respect to the processor clock. They can occur at any time because they are not dependent on the CPU. They are their own entity. Okay? So consequently, the kernel can be interrupted at any time to process interrupts. An interrupt is physically produced by electronic signals originating from hardware devices and directed into input pins on an interrupt controller, a simple chip that multiplexes multiple interrupt lines into a single line to the processor. So now, with that complication, it's not just this anymore. So rebuilding our mental model of a computer, we'll have the CPU, we'll have RAM, Okay, now we have an interrupt controller, which is it like this? Is that how you spell it? I don't know. You know what I mean. An interrupt controller that then takes all these signals coming in from devices. So let's just say this is like IO device. This is like PCIe. Okay, this would be like your GPU, net, and so on. Right? So these guys send signals to the interrupt controller. The interrupt controller will then send interrupts to the CPU. Okay, so here, this is hardware. So that's like another separate chip. Okay. Is that? Yeah. Okay. So upon receiving an interrupt, the interrupt controller sends signals to the processor. The processor detects this signal and interrupts its current execution to handle the interrupt. The processor detects this signal and interrupts its current execution to handle interrupt. So the interrupt is always important. The processor can then notify the operating system that an interrupt has occurred, and the operating system can handle the interrupt appropriately by running the interrupt handler or the function. Different devices can be associated with different interrupts by means of a unique value associated with each interrupt. This way, interrupts from the keyboard are distinct from interrupts from the hard drive. So different devices can be associated with different interrupts by means of a unique value associated to each interrupt. So it's going to be an interrupt ID, or like the device to an interrupt ID. So every device has like some sort of different ID that can be keyed in on to understand which device is actually sending that interrupt. So that's the reason why like a keyboard interrupts are different from a hard drive's interrupts just by being able to key them in. So this enables the OS to differentiate between interrupts and to know which hardware device caused which interrupt. So like if you actually go on Linux, what I mean by that is if you go to procfs, you cat proc, I think it's called interrupts, you'll actually see a lot of data coming back, right? But if you take a look at these things here, these are actually IDs of a specific we're here, like interrupt device. So take for example, we have interrupt 8. That's the RTC. That's going to be the real-time clock. And then you also have things like, I don't know, let's see, is there something like NVMe, right? Like these are disk related interrupts. So my NVMe drive will send interrupts with 54, and then here's my graphics card here will send interrupts with ID 53. So if I had an interrupt coming from 53, then I would know that it's coming from an NVIDIA graphics card. I think some of these are like typical. For example, take interrupt 8 for instance. That's usually the RTC in this case. So yeah, I have a lot of stuff here. It's a lot of stuff because my motherboard's one of those workstation motherboards. So anyway, in turn, the operating system can service each interrupt with its corresponding handler. These interrupt values are often called interrupt requests or IRQ lines. So interrupt values, so an IRQ line is like 8 for the RTC, and for a graphics card, for example, in my case it was like 53 or something like that. So this would be like ID 53, so interrupt line 53 for GPU, and then maybe for disk it was like 54, and maybe there was like a RTC here, which is like going into here too, so that's probably 8, and so on. So these are interrupt lines. These IDs are interrupt lines. Okay, each IRQ line is assigned a numeric value. For example, on the classic PC, IRQ 0 is the timer interrupt and IRQ 1 is a keyboard interrupt. Not all interrupt numbers, however, are so rigidly defined. Interrupts associated with device on the PCI bus, for example, generally are dynamically assigned. So yeah, so this 53 here for my GPU isn't always going to be 53 on your computer. Just so happens on my computer, it's 53. So other non-PC architectures have similar dynamic assignments for interrupt values. The important notion is that a specific interrupt is associated with a specific device, and the kernel knows this. The hardware then issues interrupts to get the kernel's attention. So interrupt is kind of like telling the kernel, hey, I have a new key press waiting. Read and process these bad boys. Because the hardware can't maintain that state for too long. So interrupts will tell the OS, or at least the CPU to tell the OS, hey, handle this thing, this piece of data coming in from the device right now. So. Okay. Exceptions. So exceptions. Yeah. In OS texts, exceptions are often discussed at the same time as interrupts. Unlike interrupts, exceptions occur synchronously with respect to the processor clock. Indeed, they are often called synchronous interrupts. Exceptions are produced by the processor while executing instructions either in response to a programming error, for example, divide by zero, or abnormal conditions that must be handled by the kernel, for example, a page fault. Okay, so I'm going to really make sure we understand this part here. So, exceptions are kind of like interrupts, but except that these things are coming from the processor, whereas the interrupts come from the hardware, right? Interrupts come from the hardware, while exceptions come from the CPU. So, these are like pretty much programmatic errors. Okay. Because many processor architectures handle exceptions in similar manner to interrupts, the kernel infrastructure for handling the two is similar. Much of the discussion of interrupts, asynchronous interrupts generated by hardware. So interrupts are considered asynchronous. So these are async interrupts because they can happen at any time. Can happen anytime. Because you're not in control of it. It's the hardware. Okay? And these are synchronous interrupts, synchronous exceptions. Because it's coming from the CPU and it's all like everything's always processed in the CPU, so the CPU kind of knows that that's happening anyway. It's expecting it. So, okay, so you are in this chapter, much of the discussion of interrupts, asynchronous interrupts generated by hardware in this chapter also pertains to exceptions, which are synchronous interrupts generated by the processor. So again, interrupts are generated by the hardware. Exceptions are generated by the processor. You are already familiar with one exception. In the previous chapter, you saw how system calls on the x86 architecture are implemented by the issuance of a software interrupt, which traps into the kernel and causes execution of a special system call handler. Interrupts work in a similar way. You will see, except hardware, not software, issues interrupts. Okay, so remember that the whole system call thing where we had to like fake a trap and then or issue a trap and then have like the CPU tell the OS like, hey, like there's a system call that's happening. Well, that's a form of an exception. Okay, so a system calls is like one of those types of exceptions that happen, and that's all by software, right? It's triggered through software. Similar to how divide by zero would cause a trap, and that's also by software. Hardware is basically where those devices will generate those interrupts. So the asynchronous version. Or let me say that better. Okay, so usually exceptions are generated through software on the processor, while the hardware interrupts are generated by the devices, right? So, and those are async. Okay. Interrupt handlers. The function the kernel runs in response to a specific interrupt is called an interrupt handler. The function the kernel runs in response to a specific interrupt is called an interrupt handler. So an interrupt handler is, again, a function that is run to respond and handle a specific interrupt. Okay. We also call interrupt handlers interrupt service routines, or ISR. So an interrupt is called an IRQ, interrupt request, and the interrupt handler is now sometimes called an interrupt service routine, or an ISR. So you have IRQs and ISRs. Each device that generates interrupts has an associated interrupt handler. So every interrupt has an associated interrupt handler. For example, one function handles interrupts from the system timer, whereas another function handles interrupts generated by the keyboard. So every interrupt has an interrupt handler. The interrupt handler for a device is part of the device's driver. So the interrupt handler is registered, pretty much assigned by code, the driver of that hardware. So that's also in the kernel. Drivers are implemented in the kernel, or in the kernel or in kernel code. Could be loaded through, statically, meaning compiled with the kernel, or loaded modularly. So the kernel code that manages the device. Okay, so in Linux, interrupt handlers are normal C functions. They match a specific prototype, which enables the kernel to pass the handler information in their standard way, but otherwise they are just ordinary functions. So all interrupt handlers must have that same function prototype, so that the signature always has to be the same. So it's like an interface. So you just need to implement some sort of function that has that same signature, like taking the same arguments, argument types, the number of arguments, and then with the return value and the return value type. Then you can call it an interrupt handler. It will just be run by the OS in this case. Okay, so it's like object-oriented programming. What differentiates interrupt handlers from other kernel functions is that the kernel invokes them in response to interrupts, and that they run in a special context. We discuss this later in this chapter. The special context is called the interrupt context. So remember, we had something called process context, and we also have something called interrupt context. Process context is basically when the kernel is executing system calls. Those system calls are on behalf of the process. Well, when the kernel is executing an interrupt handler, or an ISR, it's actually executing on behalf of that interrupt or the piece of hardware. So that's why we call that interrupt context. So the special context is occasionally called atomic context because, as we shall see, code executing in this context is unable to block. Okay, unable to block. So yeah. In this book, we will use the term interrupt context. So, So what does this mean? Executing is unable to block, because code inside the interrupt context has to run basically atomically, so it has to go from start to finish. Okay. Because an interrupt can occur at any time, an interrupt handler can in turn be executed at any time. Because an interrupt can occur at any time, an interrupt handler can, in turn, be executed at any time. It is imperative, basically important, that the handler runs quickly to resume execution of the interrupted code as soon as possible. So interrupt handlers must run as quickly as possible so that you can actually go back to what you were really doing before you were interrupted by the piece of hardware. So you say, just finish what you're doing, just get it done, and get out. So go back to what you were doing. Therefore, while it is important to the hardware that the operating system services the interrupt without delay, so it's important that we handle interrupts as quickly as possible. It is also important to the rest of the system that the interrupt handler executes in as short of a period as possible. At the very least, an interrupt handler's job is to acknowledge the interrupt's receipt to the hardware. Hey hardware, I hear you, now get back to work. Okay, so basically minimally, when an interrupt occurs and then you have to execute an interrupt handler, the very least you can do like if you really really want to go really fast and execute the interrupt handler super like fast, is that you can just hack the hardware saying, hey hardware, I got it, don't worry, just go continue doing what you've been doing. I got your interrupt, I'll do it later, right? So you just return right away. Okay. And that the work that you're supposed to do with that data from the hardware when an interrupt happens, you can actually execute it at a later time by scheduling it. So, and I think they're going to talk about that. So often however, interrupt handlers have a large amount of work to perform. Yeah, so it's like not every device can just handle that, right? Like you can't just say, hey, I got you, keep doing what you've been doing, device. Because like for example, if you have like I don't know, graphics or like network, you have a lot of data to process when that interrupt occurs. So what do you do then? So yeah, the book is going to go to that. It's like to how to handle these situations. So for example, consider the interrupt handler for a network device. On top of responding to the hardware, the interrupt handler needs to copy networking packets from the hardware into memory, process them, and push the packets down to the appropriate protocol stack or application. Obviously, this can be a lot of work, especially with today's gigabit and 10 gigabit Ethernet cards. Okay, so top halves versus bottom halves. So this is it. This is like how you would be able to handle interrupts quickly, but then take that data that happened in that interrupt and save it for later to execute while taking your time doing so. So top halves versus bottom halves. These two goals that an interrupt handler execute quickly and perform a large amount of work clearly conflict with one another. So how can you actually do a lot of work but also execute really fast? It's kind of hard, right? So because of these competing goals, the processing of interrupts is split into two parts or halves. The interrupt handler is the top half. So the interrupt handler, the interrupt service routine, ISR, or the function that handles interrupts, so all mean the same thing. We call this the top half. The top half. That part is where you're supposed to execute as quickly as possible. It could be as simple as just saying, hey, ack, got you, come back. Or go back to what you were doing. So that's the top half. The top half is run immediately upon receipt of the interrupt and performs only the work that is time critical, such as acknowledging receipt of the interrupt or resetting the hardware. Work that can be performed later is deferred until the bottom half. So this is where you do your heavy duty processing. The bottom half runs in the future at a more convenient time with all interrupts enabled. So basically, when you run the bottom half code, that part you can run outside of interrupts context, okay? So you can just take your time to run that as like normal code, and yeah, this is where you can do all your heavy duty processing. So Linux provides various mechanisms for implementing bottom halves, and they are all discussed in Chapter 8, Bottom Halves and Deferring Work. Okay, so now we know there's a top half and a bottom half to handling interrupts. Interrupt handlers are usually done in the top half, and then bottom half is just the processing of the data involved that happened during the interrupt. So, and that's deferred usually. So now, let's look at an example of the top half, bottom half dichotomy using our old friend, the network card. So they're going to use a network card as an example. When network cards receive packets from the network, they need to alert the kernel of their availability. They want and need to do this immediately to optimize network throughput and latency and avoid timeouts. Thus, they immediately issue an interrupt. Hey kernel, I have some fresh packets here. The kernel responds by executing the network card's registered interrupt. Okay, so it'll run the interrupt handler to get those fresh packets from the network card, because the network card has packets to deliver to the computer, to the CPU, so it has to issue an interrupt to the CPU. CPU interrupts the OS and say, hey, network card has a lot of stuff you need to pick up. So then kernel will then just say, okay, yeah, got it. I'm going to pick it all up. But it's not doing anything with it yet. It just handles that and goes, network card, go back to what you're doing. Okay, so then the interrupt runs, acknowledges the hardware, copies the new networking packets into main memory, and readies the network card for more packets. So that's what it's doing. That's the top half, I think. Yeah. These jobs are the most important, time critical, and hardware specific work. The kernel generally needs to quickly copy the networking packet into main memory because the network data buffer on the networking card is fixed and minuscule in size, particularly compared to main memory. So yeah, because packets are coming into the network card, but the network card has like a buffer, like memory there to hold. If the kernel doesn't pick all that up right away, that buffer can overflow, losing data in the process. So that's the reason why the kernel has to pick that up and put it into memory somewhere for the time being on the computer, and let the network card say, hey, okay, I got your packets. You can just clear your buffer and take in more data from the internet or something. Okay. And that's the reason why if you have like a very fast network card, but you don't have enough CPU power to do all this work, then you get very unreliable networking, right? And that's the reason why also like having lots of RAM helps too if you're just receiving so much data at such high bandwidth. So okay, so delays in copying the packets can result in a buffer overrun, with incoming packets overwhelming the network card's buffer and thus packets being dropped. After the networking data is safely in main memory, the interrupt's job is done, and it can return control of the system to whatever code was interrupted when the interrupt was generated. The rest of the processing and handling of the packets occur later in the bottom half. So like, you know how like we had that OSI stack where you receive the data packets and now you want to kind of go up the stack up back to the application layer. That's done all later, not in the ISR. So in the interrupt handler, that's all top half stuff. So in this chapter we look at the top half, and the next chapter we study the bottom half. Okay. Ooh, maybe some code. I don't know. Let's see. Registering. Bro, my screen went blank. Okay. So registering an interrupt handler. Interrupt handlers are the responsibility of the driver managing the hardware. Okay, so interrupt handlers come from the driver. So the code for interrupt handler is from the driver. Each device has one associated driver, and if that device uses interrupts, most do, then that driver must register one interrupt handler. Drivers can register an interrupt handler and enable a given interrupt line for handling with the function request with the function request IRQ, which is declared in Linux interrupt.h. So this is the function that is called when a driver wants to register an interrupt handler to the kernel. This is the function request IRQ. You pass in the interrupt number, I'm guessing. So we had a GPU, NVIDIA GPU, it would have been the 53 here. Pass in the 53, pass in the handler code, right? This is a function pointer, most likely down here. It shows it right there. That's the interrupt handler. Bunch of flags, and I think this is like a label for it, like a name. And then we'll get to this dev pointer later. So let's see that in code. So we do this, and then we look for interrupt.h. Let's see, yeah. We'll see that we say requests IRQ. Okay, so this is the one. Yeah, so this is the one. Okay, that's just the declaration. So I wonder if we have an well, let's see how many people actually use this. So request IRQ. Yeah, so you see a lot of devices are actually doing this. So you have like, for example, I don't know. Wow, yeah, 2,353 things. Okay, so you have RTCs doing that. You also have, looks like sound cards, right? You see sound cards are actually doing the request RQ stuff to register. What else do we have? Yeah, you have a lot of devices. Like one of the devices I want to show you is like the keyboard, right? So PS2 keyboard is like i8042 or something like that. So then we can just look for, I guess, the driver for the PS2 keyboard. I think it's i8042.c. Yeah. So right here is the driver to a PS2 keyboard, and then you look at request IRQ here. You'll see that it's registering what is it? IRQ. So ISR to the IRQ. So take for example, like this one here is this is like the initialization code, set up the keyboard, right? So this is keyboard. This is literally the thing that we're typing with right now. You kind of look at the definition here, the key KBD IRQ, it's 1. So usually for a PS2 keyboard, that IRQ is 1. And so if you were to go back, how do I go back? Request IRQ request. Oh, it's not even here. So it's the other buffer. Okay, there we go. Okay, so here, this is the IRQ name, right? So, and then, what am I? Yeah, this is the IRQ name, okay? And then this one would be the IRQ, like the ISR, the interrupt handler. So the interrupt handler here, I don't even know where that goes to. It doesn't, GD doesn't seem to work. So let's search for it. I8042 interrupt. Okay, so right there, maybe it's implemented somewhere else. Let's see. Right there. So, oops, right here. So this is the interrupt handler, this code here. Okay, so all this code runs whenever we kind of just press a key on the keyboard. Okay, and because every time we press a key on the keyboard, that issues an interrupt, and then when an interrupt occurs, the CPU or the kernel will then look up, okay, what is the interrupt handler for interrupt number 1? In this case, it's going to be the I8042. Then execute the appropriate interrupt handler for that interrupt, which is going to be this function here because it was registered up in the driver. And so you see how it's kind of like just doing stuff and it gets like the data from the keyboard, right? And then it does more stuff here. So like not too important to understand, but just know that there is a flow to this. So yeah, that's how we register. So the first parameter, IRQ, specifies the interrupt number to allocate. For some devices, for example, legacy PC devices such as the system timer or keyboard, this value is typically hard-coded. For most other devices, it is probed or otherwise determined programmatically and dynamically. The second parameter, handler, is a function pointer to the actual interrupt handler that services this interrupt. This function is invoked whenever the operating system receives an interrupt. Okay, so yeah, let's take a look at this function pointer. Okay, let's look at what it is. So basically, it takes in 2 arguments. This function pointer takes in 2 arguments. First, an integer. Next, a pointer to a void. Okay, and it returns IRQ return T. Okay, so if we were to go back to here, our friend, the keyboard interrupt handler, notice how it takes in 2 arguments, right? An int and a pointer to a void, just like what it was defined, and returns an IRQ return T. So it adheres to this function prototype, whatever signature. So note that the specific prototype of the handler function, it takes 2 parameters and has a return value of IRQ return T. I just repeated that. This function is discussed later in this chapter. Okay. So interrupt handler flags. The third parameter flags can be either 0 or a bit mask of 1 or more of the flags defined in Linux interrupt.h. Among these flags, the most important are IRQF disabled. When set, this flag instructs the kernel to disable all interrupts when executing this interrupt handler. When unset, interrupt handlers run with all interrupts except their own enabled. Okay, wait, hold on. Let's digest this. When this flag is set, IRQF disabled is true. This flag instructs the kernel to disable all interrupts when executing this specific interrupt handler. When it is unset, interrupt handlers run with all interrupts on except with their own enabled. So their interrupt line is disabled while all the other interrupts are still flowing. Okay? But if you disable all interrupts, meaning that when you're executing, when your interrupt handler is executing, all other interrupts cannot happen in the system at that point. Okay? Yeah, so basically whenever your interrupt happens, especially for a specific device, that interrupt line is, I think, becomes disabled. So the kernel and the CPU isn't accepting any more interrupts while handling the current interrupt for that device, just for that device. So very device specific. So we go back to here. Let's say the GPU executes or issues an interrupt, for example, here, right? So that means this becomes blocked, and then only this one gets to flow through. Yeah, so at least that's my understanding so far. Of course, we can always tweak our knowledge. Okay, so most interrupt handlers do not set this flag, as disabling all interrupts is bad form. Its use is reserved for performance sensitive interrupts that execute quickly. This flag, so we don't usually set this flag, basically. So this is what they're saying. This flag is the current manifestation of the SA_interrupt flag, which is in the past distinguished between fast and slow interrupts. Not sure what that means, but okay. IRQF sample random. This flag specifies that interrupts generated by this device should contribute to the kernel entropy pool. Okay. The kernel entropy pool provides truly random numbers derived from various random events. Oh, it contributes to being able to calculate random numbers, I guess. If this flag is specified, the timing of interrupts from this device are fed to the pool as entropy. Do not set this if your device issues interrupts at a predictable rate. Yeah, because that will cause your entropy to be more ordered, I guess, so you get less randomness when you generate random numbers. For example, the system timer, or can be influenced by external attackers, for example, a networking device. On the other hand, most other hardware generates interrupts at non-deterministic times and is therefore a good source of entropy. IRQF timer. This flag specifies that this handler processes interrupts for the system timer. IRQF shared. This flag specifies that the interrupt line can be shared among multiple interrupt handlers. So you can actually register multiple interrupt handlers to a specific interrupt line. So in this case, when we had our keyboard here, it's not just that one handler that can be registered. We also saw that it could be registered against, we can register multiple handlers to that interrupt line. So each handler is registered on the given line must specify this flag. So you have to specify that if you want to do that. Otherwise, only one handler can exist per line. More information on shared handlers is provided in the following section. Okay, let's see what in code what the keyboard handler actually did. So register IRQ, or is it request IRQ? Sorry. Oop. Request IRQ, and that's for aux, whatever that means. I want the KBD. Okay, so it's IRQF shared. So it is able to share multiple handlers in that same line here, the I8042KBD IRQ. Okay, so now let's keep going. The fourth parameter name is an ASCII text representation of the device associated with the interrupt. For example, this value for the keyboard interrupt on a PC is keyboard. Okay, keyboard, literally. Okay, so these text names are used by proc IRQ and proc interrupts for communication with the user, which is discussed shortly. Okay, so whenever we do the cat proc interrupt, for example, these names here are the names. Like these labels here are the names that are passed in. So yeah. In this case, if we were to go back to, was it 53? That's NVIDIA. So NVIDIA was passed in. Okay. I think I don't have a interrupt 1 or i8042 because of my keyboard. I don't have like a typical keyboard. I'm one of those ergonomic ones through USB-C. So maybe that's the reason why. Yeah. So the fifth parameter, dev. Okay, so this is the one that we weren't sure about. What is this thing here, right? A pointer to avoid, dev. Okay, so let's read this carefully. The fifth parameter, dev, is used for shared interrupt lines. When an interrupt handler is freed, discussed later, so you can release memory, right? Dev provides a unique cookie, so basically a key or token that's associating things to enable the removal of only the desired interrupt handler from the interrupt line. So since if you can have multiple interrupt handlers associated with the interrupt line, you actually don't know which interrupt handler to remove on the interrupt line, right? You lose that information. So dev is that token, that cookie that you can use to pass when you're registering an interrupt handler to an interrupt line, and keep that dev around. And when you're ready to kind of pull it out just to delete that specific handler, you can pass in that dev again. So that's how we can differentiate. So without this parameter, it would be impossible for the kernel to know which handler to remove on a given interrupt line. You can pass null here if the line is not shared, okay? So it's not always required, but you must pass a unique cookie if your interrupt line is shared. And unless your device is old and crusty and lives on the ISA bus, there's a good chance it must support sharing, like PCI. This pointer is also passed into the interrupt handler on each invocation. A common practice... Oh, okay, so it's always passed in every time your interrupt handler runs. Okay, that's good to know. A common practice is to pass the driver's device structure. This pointer is unique and might be useful to have within the handlers. Oh, okay, so it's just basically anything. It could be like a string too. Okay. On success, request IRQ returns 0. A non-zero value indicates an error, in which case the specified interrupt handler was not registered. Okay, makes sense so far, standard stuff. A common error is negative error busy, which denotes that the given interrupt line is already in use and either the current user or you did not specify RQF shared. Okay, so when you register an interrupt handler, if it returns 0, that's fine. But if it's non-zero and you get this eBusy error, it just means that you didn't pass IRQF shared, and chances are you're registering an interrupt handler against an interrupt line that already has an interrupt handler associated with it. So you can't stack it like you would if you enabled this flag here. Okay, cool. Okay, so note that request IRQ can sleep and therefore cannot be called from interrupt context or other situations where code cannot block. It is a common mistake to call request IRQ when it is unsafe to sleep. This is partly because of why request IRQ can block. It is indeed unclear. On registration, an entry point corresponding to the interrupt is created in proc IRQ. The function procMakeDir creates new procfs entries. This function calls procCreate to set up the new procfs entries, which in turn is called kmalloc to allocate memory. As you will see in chapter 12, memory management, kmalloc can sleep. So there you go. Okay, so when you're allocating memory, there's a chance that you can end up going to sleep. So you have to make that assumption that it's not safe to assume that request IRQ is atomic. In this case, it can go to sleep. Okay, interrupt example. In a driver requesting an interrupt line, and installing its handler is done via the request IRQ. So right here, this is how you actually hook up an interrupt handler to a specific interrupt line. So in this case, my interrupt is that function, and IRQN is that interrupt line. Specify what IRQ I've shared with the name my device, and my dev as the cookie token to actually be able to retrieve back the handler, or like give the kernel code the ability to differentiate the handler in that line where potentially there will be multiple handlers in there. Okay, so we saw that in i8042.c. So it's the same thing. So going back to here, going back to here, see, request IRQ and error. You see this error? If non-zero, go to whatever this is, the error handling code. Okay, so in this example, IRQN is the requested interrupt line. My interrupt is the handler, and we specify via flags that the line can be shared. The device is named my device, and we passed my dev for dev. On failure, the code prints an error and returns. If the call returns 0, the handler has been successfully installed. From that point forward, the handler is invoked in response to an interrupt. It is important to realize hardware and register an interrupt handler in the proper order to prevent interrupt handler from running before the device is fully initialized. Okay, freeing an interrupt handler. When your driver unloads, you need to unregister your interrupt handler and potentially disable the interrupt line. To do this, call freeIRQ. If the specified interrupt line is not shared, this function removes a handler and disables the line. Okay, let's read this again. When your driver unloads, meaning that your driver is done, like out of memory, you need to unregister your interrupt handler. So unregister the function that you stuck in somewhere to that IRQ line and potentially disable the interrupt line. To do this, call freeIRQ with the interrupt line and that cookie token. If the and this cookie token is going to be used to figure out, okay, well, based off of this information, which handler is associated with this cookie and this line here. So if the specified interrupt line is not shared, this function removes a handler and disables the line. Okay, meaning because that's the last handler in that line, so just disable the line. If the interrupt line is shared, the handler identified via dev is removed, but the interrupt line is disabled only when the last handler is removed. So we only disable the interrupt line when we remove the last interrupt handler in that line. So now you can see why a unique dev is important. With shared interrupt lines, a unique cookie is required to differentiate between multiple handlers that can exist on a single line and enable freeIRQ to remove only the correct handler. In either case, shared or unshared, if dev is non-null, it must match the desired handler. A call to freeIRQ must be made from process context. Okay. So here, interrupt registration. So request IRQ registers a given interrupt handler on a given interrupt line. FreeIRQ will unregister the given interrupt handler. If no handlers remain on the line, the given interrupt line is disabled. Okay, so this is how we're going to write interrupt handler, but I think we won't have that much time to do it. So I'm going to instead kind of just show you this KBD thing. So for example, let's say we want to, just print out whatever was in data, or let's prove that on every keystroke, at least this KBD interrupt handler runs, right? So first of all, like maybe we can do something like this where so basically it requests IRQ, it registers, so we can just say something like this, print K, current info, average dev, registering I8042 interrupt handler to KBD to IRQ, right? And this will be integer, and this will be I8042 KBD IRQ. So this should only happen once, okay? So right there when we register, and then let's go to the I8042 interrupt. So if we were to go to the other buffer, I think. No, that's the definition. Let's see, I8042 interrupt. Right here? Or no, not there. Right here. Okay. So here, at some point, it's going to grab some data right here, right? So this is unsigned char. So it's just basically going to be a simple print that says, I don't know, the data read from KBD. Okay, so we could just do, how do we output hex? Oops. Print FC output hex. Oh, 0x percent 02x for 2 hexadecimals. Okay. Percent 02x. Okay, I'll remember that. Okay, percent 02x. That's how we're gonna do it. Okay, and that'll take in the data. Okay. So we'll have that. So every time we hit a key, it's going to print out the data that's being read because this is the interrupt handler from I8042. How I know to do this is because my VM, which is going to be here, I already spoiled it. That was from something else. Okay, so my keyboard is actually oops. Okay, if I were to go and look at interrupt 1 here, it's the I8042. So I do have it, and obviously I do. Okay, so I have that. I just have basic code to print out two things. First, registering that IRQ on the I8042, and then basically whenever a keystroke happens, an interrupt request occurs, and this handler associated with that interrupt request will execute this print statement here, and we can actually figure out what we're typing. Okay, it's just a simple flow. So if I were to go and compile this, it's not sudo, just make J24. It should get to pretty close to what I want. So just so you know, the data that is being output by I8042 is going to be not ASCII. It's something else. It's like I8042 key codes or something like that. There's like a spec for this, like specific. Oh man. What is this? There's like specific numbers associated with it. Maybe here. No, this is not it. Oh, or is it? Let's see. This is escaped. I want like letters. Oh, it's all here. Wow. I want like a nice table. where can I find it? Let's see. You know what? Oops, not this one. Let's just do this one. This one's here. It's all here. So like, for example, like, I don't know, like 2C would be Z, right? 2D would be X, and so on. And then if we see something like, what's it, L shift? What's L shift? Shift left. Well, anyway, like we had something like shift, you would see like this number followed by 2D would be a capital X, for example. So we'll just go by this when we're testing. Oh, still doing it. It's a good way for me to also like rest my voice. So, but should I keep going? No, I don't want to. No. 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 I should, however. Yeah, let's just do it. Okay, let's just do it. Alright, so writing an interrupt handler. The following is a declaration of an interrupt handler. Static IRQ return T interrupt handler int pointer to avoid. Right, so handler will take in the dev. So going back to here, you see this handler took a dev. And where was this dev from again? Let's see. Originally, right there, it's just the i8042 platform device. So let's just kind of look at that. Where is that? Okay, dev. Okay, where's dev coming from? Oh, yeah, so it's the struct platform device. So it's whatever is passed into here. So that's okay. That's what the book said too. Okay. So note that this declaration matches the prototype of the handler argument given in the request IRQ. The first parameter IRQ is a numeric value of the interrupt line that the handler is servicing. This value is passed into the handler, but it is not used very often. So this one is not used very often, except in printing log messages. Before version 2.0 of the Linux kernel, there was not a dev parameter, and thus IRQ was used to differentiate between multiple devices using the same driver and therefore the same interrupt handler. As an example of this, consider a computer with multiple hard drive controllers of the same type. Whoa, that doesn't sound very reliable. The second parameter dev is a generic pointer to the same dev that was given to request IRQ when the interrupt handler was registered. If this value is unique, which is required to support sharing, it can act as a cookie to differentiate between multiple devices potentially using the same interrupt handler. Dev might also point to a structure of use to the interrupt handler. Because the device structure is both unique to each device and potentially useful to have within the handler, it's typically passed for dev. So it's like it can also be used as like context, right? Like state for your device that you can just pass around, which is handy. So it could be a pointer to a struct instead of a pointer to a void. You just have to cast it as like a pointer to a struct in this case. A pointer to a void, sorry. The return value of an interrupt handler is a special type IRQ return T. An interrupt handler can return two special values, IRQ none or IRQ handled. So the interrupt handler in here is returning either interrupt none or interrupt handled. So was it I8042? What was it? What was it called? Shoot. What was that interrupt handler called again? Right here. I8042 interrupt. Or is it here? Right there. So here, it's returning what? Yeah, and IRQ return value. Sure. What else is a return? Go to out. Interesting. Oh wait. I think that's it. Yeah, this is the one. Given some sort of return value, I think there's a macro. Yeah, okay. It will determine whether or not it's IRQ handled or IRQ none. Okay, yeah. The former is returned when the interrupt handler detects an interrupt for which device was not the originator. The latter is returned if the interrupt handler was correctly invoked, so you kind of always want this. And its device did indeed cause the interrupt. Alternatively, IRQ ret val may be used. If val is non-zero, the macro returns IRQ handle. Okay, if it's non-zero, okay, that's a good sign. Otherwise, the macro returns IRQ none. That's if it's zero. These special values are used to let the kernel know whether devices are issuing spurious, that is, unrequested interrupts. If all the interrupt handlers on a given interrupt line return IRQ none, then the kernel can detect the problem. Note the curious return type, IRQ return T, which is simply an int. This value provides backward compatibility with the earlier kernels, which did not have this feature before 2.6. Interrupt handlers returned void. That's probably not a good thing, huh? Drivers may simply type def IRQ return T to void and define the different return values to no ops and then work in 2.4 without further modification. The interrupt handler is normally marked static because it is never called directly from another file, so it's private pretty much. The role of the interrupt handler depends entirely on the device and its reasons for issuing an interrupt. At minimum, most interrupt handlers need to provide acknowledgement to the device that they received the interrupt. Devices that are more complex need to additionally send and receive data and perform extended work in the interrupt handler. As mentioned, the extended work is pushed as much as possible into the bottom half handler, which is discussed in the next chapter. Looks like it's done. Huh? Oh, not yet. Okay. Go on. Okay, so reentrancy and interrupt handlers. Interrupt handlers in Linux need not be reentrant. Okay, so top half, interrupt handlers need not be reentrant. When a given interrupt handler is executing, the corresponding interrupt line is masked out on all processors. Okay, so basically the interrupt line is disabled. Basically, when you're processing an interrupt with the interrupt handler, for all other CPU cores where it's connected to the interrupt controller, they do not they also don't receive any more interrupts on that interrupt line, so as long as you're still processing stuff. Okay, so that prevents another interrupt on the same line from being received. Normally all other interrupts are enabled, so other interrupts are serviced, but the current line is always disabled. Consequently, the same interrupt handler is never invoked concurrently to service a nested interrupt. Okay, this greatly simplifies writing your interrupt handler, so you could assume it's single thread in this case. Okay. Shared handlers. A shared handler is registered and executed much like a non-shared handler. Following are three main differences. The IRQF shared flag must be set in the flags argument to request IRQ. The dev argument must be unique to each registered handler. A pointer to any per device structure is sufficient. A common choice is the device structure as it is both unique and potentially useful to the handler. You cannot pass null for a shared handler, so you can't for that dev cookie thing. If you're registering another handler on a line that already has a handler existing, you can't just pass null, but you can if it's the only one. Okay, we're almost there. All right. So the interrupt handler must be capable of distinguishing whether its device actually generated an interrupt. This requires both hardware support and associated logic in the interrupt handler. If the hardware did not offer this capability, there would be no way for the interrupt handler to know whether its associated device or some other device sharing the line caused the interrupt. All drivers sharing the interrupt line must meet the previous requirements. If any one device does not share fairly, none can share the line. When request IRQ is called with IRQF shared specified, the call succeeds only if the interrupt line is currently not registered or if all registered handlers on the line also specified IRQF shared. Shared handlers, however, can mix usage of IRQF disabled. When the kernel receives an interrupt, it invokes sequentially each registered handler on the line. Therefore, it is important that the handler be capable of distinguishing whether it generated a given interrupt. The handler must quickly exit if its associated device did not generate the interrupt. Okay, so this is important. When the kernel receives an interrupt, it invokes sequentially each registered handler on the line. So it goes one by one. Okay. Therefore, it is important that the handler be capable of distinguishing whether it generated the given interrupt. So the handler has to know if it belongs to itself. That's where dev comes in, right? The handler must quickly exit if its associated device did not generate the interrupt. This requires a hardware device to have a status register or similar mechanism that the handler can check. Most hardware does indeed have such a feature. Okay. All right. Cd make install. Cd update grub. Okay, let's reboot. I probably don't even need to call this all the time. It's the same kernel version anyway. I realized that. Oops. Oh wow, I've been going for a while. Okay. So we'll demessage the registration in the handler, and then we'll do a demo on seeing like the logging after each keystroke, and then I think I'll call it. So. And what was the logging that we did? Let's see. Average dev. So registering. We'll look for this. So we'll grep for registering I8042 interrupt. So if we did demessage, and we can just do grep registering. Was it average dev? Can we just do it like this? Maybe. Oops. There we go. So we registered very early on. Wow, 3 seconds in. I guess that's what it is. And then if I were to just type, let's say, what was it? Keyboard scan code. Let's do something like V. So we'll see 2F a lot. So let's just do like just hold down V, and then we'll see it. So we did V, something like that. Just like type it like no other, right? And then we did that. The message. I shouldn't have pressed enter, but right here, you see all this 2F, right? That's basically This case, for I8042, it's V. If I were to zoom that in, sorry, I didn't realize. Okay, right there. Yeah. Okay. You know what? Let's fix this. It shouldn't be this way. You all can't suffer like this. Let's do 24. Okay. So if there we go. That should be better. Okay. Okay, cool. So that's it. Thanks.